This section deals with the concept of gravitational potential energy, and we start by examining the work done by the gravitational force. The force due to gravity can do positive or negative work. In the case of a ball falling downward, the force of gravity, mg, does positive work on the ball as it moves through a displacement s from height h0 to height hf. In this case, the work done by gravity equals mg cosine theta times h0 minus hf, where theta equals 0 and cosine of theta equals 1. Notice that the work done depends only on the difference in heights, h0 minus hf. The path through which this difference in height occurs does not matter. We say then that the work done by the gravitational force in this case is path independent. Since we now have the work done by the gravitational force, we can use the work-energy theorem to find the change in kinetic energy of an object that falls through a distance h0 minus hf. For example, suppose an object of mass m equals 2.0 kilograms falls from rest from a height of 5.0 meters. What is its final kinetic energy? We know that the work done by the gravitational force in this case is W equals mg times h0 minus hf, where h0 minus hf equals 5.0 meters. So the work equals 2.0 kilograms times 9.8 meters per second squared times 5.0 meters, which equals 98 joules. Now, using the work-energy theorem, we know that the work done equals the change in kinetic energy, or W equals KEF minus KE0. Since the object started from rest, we know that the initial kinetic energy equals 0, or the work is just equal to KE final, which equals 98 joules. Now, what is the speed of the ball just before it hits the ground? Since we know the final kinetic energy is given by KE final equals 1/2 mv final squared equals 98 joules, and we know the mass equals 2.0 kilograms, we solve for the speed, v final. We have v final equals the square root of 2 times 98 joules divided by 2.0 kilograms, which equals 9.9 meters per second. There are many different types of energy. For instance, as we've already discussed, an object in motion has kinetic energy. But an object can also possess another kind of energy by virtue of its position relative to the surface of the Earth, or its height. Let's go back and look at the equation we derived for the work done by gravity when moving an object from one height to another. We had W gravity equals mg h0 minus hf. We can rewrite this as W gravity equals mg h0 minus mg hf. Each of the terms on the right represents the gravitational potential energy of the object at a specific height. In other words, the work can be written as W gravity equals PE0 minus PE final, where PE stands for potential energy. A more formal definition of the gravitational potential energy goes as follows. The gravitational potential energy is the energy that an object of mass m has by virtue of its position relative to the surface of the Earth. That position is measured by the height h of the object relative to an arbitrary zero level, so PE equals mgh. The unit of potential energy is the same as that for work, kinetic energy, and all other forms of energy, the joule.